as everybody's seated as we're getting started, in order not to cut into the time of the speakers, I'd just like to give a brief introduction to this workshop, because this is part of this is a workshop that is sponsored by ICAM, the Institute for Complex Adaptive Matter, which is an umbrella organization that is focused on complex adaptive matter, and one of the things that they do is they sponsor workshops so that people who are interested in these topics can get together with senior and junior scientists to do a lot of to share work. And also one of the principal themes of these workshops is discussion. So this is something where this is a traditional format that we've got, but we've also got the poster session as well as some time buffered along the way for longer discussions. So I encourage everyone to participate, and this room will be available for the entire 2 days of the workshop, which are 4 sessions beginning with this one. I want to begin by just telling you a little bit about myself and about where you are, because I want to welcome you all to my adopted hometown. I actually live in Vancouver. I work at Simon Fraser University. I'm originally from California. I grew up in a place called Marin County, which some of you may know because of its fame in mountain biking. And one of the places where mountain biking got started was Mount Tamalpais. And Tamalpais is a word that derives from Miwok, which was the traditional people, indigenous people who lived there for millennia before settlers arrived. And in this area, we're on the unceded, shared traditional territories of a number of people: the Tsleil-Waututh, the Squamish, the Stolo, the Tsuminus, the Musqueam, and members of the Hokumenum Treaty Group. And all of these people have existed here for millennia, and long before this convention center was established, which was established for the Expo in 1986, and then grew afterwards. And so while you're here, I encourage you not just to focus on the science, which of course we're all here for, but also take a bit of time to explore the surrounding regions. It's a beautiful area, as I think you've all seen, and develop some familiarity with the culture, the present-day culture of the people who are living here now, and also some of the culture of the people who are also living here, but who have been here and been living here for thousands of years. There's 2 places that I would recommend that are not in the list of things that you might see. One is the Bill Reed Gallery, which is downtown here. Bill Reed was a Haida artist who is very famous. You might have seen his sculpture in the airport of the, basically it's a jade-colored sculpture that, if you haven't seen it, I recommend you take a look. Take some time extra time at the airport to visit it. And then there's also artwork throughout Vancouver that I think you'll appreciate. And then there's also, if you have a little bit more time to go out to UBC, there's the Anthropology Museum, which also is a great way to become familiar with the indigenous culture. So with that introduction, I'm now going to get back to the science, which is, we'll begin with Daniel Podolsky. We have a session here entirely devoted to Higgs spectroscopy. Daniel will begin with a 15-minute talk, and then we'll move to 25-minute talks, or actually 12 plus 3 and 20 plus 5. After Daniel, we'll have Rio Shimano, Dirk Mansk, and Stefan Kaiser. So,
okay. Thank you.
Please.
Thank you. So good morning. So today I want to tell you about Higgs amplification in non-equilibrium K3C60. And what I want to answer in this talk, or explore, is whether large Higgs fluctuations can be, what are basically the experimental signatures of when you have a system with large Higgs fluctuations. And so let me start by talking about K3C60. It's a superconductor with a critical temperature of 20 Kelvin. And it's made out of buckyballs that arrange in a BCC lattice with potassium atoms shown here in red that donate electrons. And here I'm showing you the optical conductivity, the real and imaginary parts, The red is equilibrium at 25 Kelvin. So you see a Drude peak that shows up both in the real and imaginary parts. That's in the normal state. At 10 Kelvin in the superconducting state, you see a spectral gap opening here because due to pairing. In the real part, in the imaginary part, you can see this 1/omega divergence that basically is a measure of the superfluid density of the material. Now, one of the things that's interesting about K3C60 is the discovery a few years ago by in the group of Andrea Cavalieri of what's called photo-induced superconductivity. The idea is that it's a pump probe experiment where you take K3C60, you shine an intense but short pulse of light, and this is followed by a measurement of the optical conductivity with a weak probe pulse. And what you see here is the, so here's 25 Kelvin, the top two panels, the real and imaginary conductivities. So red is still equilibrium, same data I showed you before with the Drude peaks. But blue is the photoexcited state. You see a significant suppression in spectral weight at low energies, perhaps due to partial pairing or pairing of the electrons. And you see this 1/omega type of divergence in the imaginary part. Okay, and this behavior still is present even at 100 Kelvin, which is 5 times the equilibrium TC. And more recent measurements, so with different a protocol for the photo excitation of the system have allowed the Cavalieri group to achieve metastability of 12 nanoseconds. So this superconducting-like behavior survives for 12 nanoseconds, which is an eternity compared to any microscopic timescale in the system. Okay, so now I want to take a step back and talk about, in general, about collective modes in a superconductor. So there are essentially two types of collective modes. Here I'm showing you the Mexican hat potential for the order parameter. And so if the system condenses here, then there's, naively you would think that there are gapless Goldstone modes associated with phase fluctuations. But because the superconductor breaks a gauge symmetry, then by the Anderson-Higgs mechanism, this Goldstone mode combines with the gapless phonons to give you just a gap mode. Okay, so you get a mode that's gapped to the plasma frequency. And this is a different way of understanding where Meissner effect comes from. On the other hand, we also have a different mode associated with fluctuations in the amplitude of the superconductivity. This is the Higgs mode. Okay, these are oscillations in the amplitude of the superconducting order parameter. So now going back to K3C60, one thing that's interesting about this is that system is that if you think about this system, starting in the normal state. So in the normal state, the potential has a single minimum for 0 order parameter, and imagine suddenly you are applying this pump pulse that's turning the system superconducting. The system suddenly finds itself in the wrong place. It's no longer at a local minimum. It's actually at a local maximum of the potential. You inverted the potential into a Mexican hat shape. And so now it has to roll down somewhere, and when it rolls down, and you expect it to overshoot and oscillate a few times above the minimum until it settles in the new minimum. And what this says is that if you're really suddenly quenching superconductivity, you expect to have very large Higgs oscillations. When I say large Higgs oscillations, I mean that you're not exciting 1 or 2 Higgs modes. You're exciting a macroscopic number of Higgs modes, which corresponds to the fact that the order parameter is sloshing around about the minimum. Okay, and so the question is, natural question is, can you see this in particular in optical conductivity measurements? And so to answer, I'll give you two complementary points of view. So one way to think about what can happen is to keep in mind that the Higgs mode, as an excitation, it can decay into pairs of photons. And there's a matrix element for such decay. This is one of the processes by which the Higgs mode relaxes. But this process is not allowed in the bulk of the superconductor. And the reason is, as I told you earlier, the photons get gapped out by the Higgs-Anderson mechanism. Okay, so this type of process can only happen near the surface. So here I'm showing you like a superconductor with this wavy line is supposed to represent a Higgs excitation in the system, and this can spontaneously decay into a pair of photons that leave the sample. So emit a pair of photons, and then there's a constraint that the sum of the frequencies of photons by energy conservation has to match the Higgs frequency. So this is some type of spontaneous decay process where any pair of photons that adds up to the Higgs frequency is allowed. But suppose that instead of allowing this process to occur spontaneously, suppose that you also are shining an incoming beam of light at some signal frequency omega s. So if you do that, what will happen now is there's a type of Bose selection. There's a Bose enhancement where you basically force the Higgs to decay into a pair of photons where one of them has to be at the energy of the incoming photons, just by Bose enhancement. Okay, so this is some type of like stimulated emission type of, that's the analogy. Okay, that you force the Higgs to decay, but the frequency of one of the photons is at the signal frequency, and then you have to emit the other photon at the complementary frequency, which I call the idler, such that the sum of the idler plus the signal is the Higgs. So what you see here is basically amplification, because you had n photons coming in and n plus 1 photons coming out. Okay. Now, of course, this is just a single photon, but this is because I'm only looking at a single Higgs mode decaying. But I told you earlier that there's basically a macroscopic number of Higgs modes, so you can achieve, you can basically achieve amplification, a true amplification of the signal by a macroscopic number of photons. So another way of looking at this is more from a nonlinear optics type of point of view. So for example, you can think about solving the Maxwell equations for electromagnetic radiation in the presence of a superconductor that has large Higgs fluctuations. So basically, these are just Maxwell's equations. And then inside the superconductor, the current satisfies the London equation. But what's new here is that usually in the London equation, this lambda is the superfluid density, which is typically time independent. But if you have Higgs oscillations, then this superfluid density has a constant part plus a part that's modulated in time at the Higgs frequency. So this is some problem of light interacting with a medium whose optical properties fluctuate in time. And so to understand how much light is reflected, you have to solve this Fresnel problem. It's called Fresnel-Fouquet because it's time periodic. And when you carry out the calculation, what you find is that the reflection coefficient, so this is the reflection coefficient as a function of a signal frequency in units of the Higgs frequency. And what you find is that the reflection coefficient exceeds 1. You get this amplification. In this case, it's like 4% amplification. You notice that the maximum effect occurs at roughly the Higgs frequency, half of the Higgs frequency. And you also notice that the signal is not very large. The amplification here is 4%. And the reason that it's not very large is that this effect is limited by the ability of the light to penetrate into the sample. If it doesn't penetrate, the probe light, if it doesn't penetrate deeply into the sample, it cannot benefit so much from the Higgs oscillations. So, and so this is due to Meitner effect. It cannot penetrate too far. So this is something that controls the size of the effect. Okay, so now the question is can this be seen in K3C60? So actually, K3C60 in a way is a very favorable material for this because it has an anomalously low plasma frequency. This means that light can relatively penetrate deeply into the sample. This low plasma frequency, 72 MeV, is low because there's a low density of electrons, and the hopping of electrons between C60 molecules is weak. And if you can compare that with like a ballpark estimation of what the Higgs frequency should be. This is an estimate coming from the onset temperature of the photo-induced superconductivity, which is so we get a ballpark figure of like 30 MeV. So these two are comparable, and that's good for Higgs amplification. Another thing that you can learn from this is that this frequency corresponds to a Higgs period of 300 femtoseconds. And why is that relevant or important? It's because now, everything that I told you was based on this picture that that you're suddenly quenching the system into a superconducting state. But let's say that if you turn on the superconductivity slowly compared to this time scale, then it's more like you are adiabatically turning on the superconductivity, at least from the point of view of Higgs oscillations. You won't get large swishing. Whereas if you do things fast compared to this, you expect really these Higgs oscillations to be large. So Okay, so here are measurements done by, again, by the group of Andrea Cavalieri. And so here I'm showing you first the results from the slow quench. Okay, the way they control the quench is just by the duration of the pump pulse. Okay, so if the pump here the pump pulse is 1.8 picosecond long, which is long compared to the 300 femtosecond Higgs period. In this case, you get that the reflectivity goes to 1, like in a normal superconductor. You don't see a Higgs amplification. But when they change the quench protocol, to the quench pulse to be 100 femtoseconds, like here, suddenly you get this Higgs amplification of the order of a few percent above 100% reflectivity. And the data, both the real and imaginary parts of the optical conductivity, are fairly well described by the simple model that I described earlier. Okay, so to conclude, I show you this Higgs amplification a phenomenon. I think it's an interesting phenomenon. It's some type of nonlinear optics type of phenomenon, but where one of the where one of the waves that's causing this nonlinear optics is really a collective mode, is the Higgs mode of the superconductor, and because of that, this is a method that can be used for spectroscopy of this collective mode. Okay, so that's one of the things that's interesting about this. It would be interesting to look for other systems with strong Higgs oscillations. I think we'll hear today about other such systems that have been studied in the lab using other probes, but I think it would be interesting to look for the same amplification. And there are other things that I didn't talk about that have not been checked experimentally that could also be strengthen the picture that this amplification seen here is really caused by Higgs, by the mechanism that I described in terms of Higgs oscillations. And I just want to end by thanking my collaborators. This was a collaboration between theory and experiment. So I want to especially thank the experimental group, Michele Buzzi, Gregor Iotsu, and Andrea Cavalieri, and also on the theory side, many close work with Eugene Demler. So thank you for your attention.
Thank you, and questions?
Yeah. So, can I ask, how fast can you make a quench? I mean, the picture you started with, you start from a minimum at 0, then you say you have a maximum at 0, so the system comes down.
Mm-hmm.
Right, and implicit to that is that you can go from this minimum at 0 to maximum on a time scale which is fast compared to the Higgs oscillation.
That's right.
Is there a theory which does that? I mean, naively, I would think that this is all just time scales associated with the magnitude of an order parameter, and you can't grow the middle peak faster than the Higgs time.
Okay, that's a good question. There's a question about, there's a question about the ultimate, low density. I think that it's a good question. I don't think there's any theory that looks at that process, and I think it's super interesting. I think that the pulse width is a lower bound on how fast it's happening, But to say that it's absolutely an interesting question, and there's no theory for that. Yeah. Yeah. Mm-hmm. Mm-hmm. Potentially, I mean, maybe. Okay. Yeah, but okay, but there's. Mm-hmm.
This means you put a lot of energy into the system.
Mm-hmm.
That's my only point I want to make. And if you put a lot of energy in the system, then we know from many other calculations that reflectivity larger than 1 means negative sigma 1, right? So
Mm-hmm.
it means radiation. So
Mm-hmm.
this means if you have a quench, you can accelerate some quasi-particles or even other,
Mm-hmm.
which will also give you photons.
Yes, it's
So
true,
did
but people have looked at that. People have looked at that in theory, but usually the radiation that you get is polarized because the currents that you get. Okay, there's a theory. There's a paper called photo-induced superconductivity without superconductivity. Okay, and it's based on the fact that non-equilibrium processes can give. Can really give currents, okay, because of this instability. But then the currents are typically perpendicular to the and then the polarization doesn't match what's in experiments.
Andrea knows more about this.
So-
Anyhow, nice piece of work.
Okay,
Thanks.
okay,
Thanks.
So, how does this work? By the room? Oh, okay, very good. So, right, so just on this, without superconductivity, they do it with the wrong optical constants. But other than that, that's a valid possibility. The question that I had, which is a bit of a comment, is this business of the oscillatory Higgs mode, the same physics, actually, we discussed this briefly yesterday, but maybe you can help me understand this better. The same physics could happen by any mechanism that makes the superfluid density time dependent.
That's for sure.
So in principle, if I go to zero temperature, and I don't necessarily excite the Higgs mode, but I drive some mode of the solid that makes the superfluid density time dependent, I might be able to get these. Amplification, right?
That's absolutely right. I mean, this is for sure not proof of the Higgs mode in this material. I think that what it does show is that there's some collective mode, something that's oscillating at a frequency that's consistent with what you would expect the Higgs frequency, but it could be other collective modes. It could even be something else that's modulating optical properties at some frequency, So I definitely think that this is a possible explanation for the experiment, but not necessarily,